going to talk about the difference between instantaneous and average by way of the term velocity. So we're going to find both instantaneous velocity and average velocity. Please give me a definition of either one. McCutcheon?
Instantaneous is your speed at one specific point in time.
Instantaneous velocity, so it would be the velocity at one specific point in time. So instantaneous velocity would be the velocity at a specific point in time. Great. Instantaneous velocity, the velocity at a specific point in time. Average velocity, Allison, will then be?
Velocity over the whole time.
It doesn't necessarily have to be the whole time, but rather a time duration, a time period. It could be the whole time, but it could just be part of the time as well. So the average velocity is the velocity over a time period, or a time duration, a certain amount of time. Difference between instantaneous and average by way of velocity. We're also going to make sure we understand this in terms of drawing a graph, figuring out various stuff about that graph. So we have the position as a function of time. We're going to have different times here. We're going to go with, this is going to be 5.0 seconds, 10.0 seconds, 15.0 seconds, and 17.0 seconds. We're also going to have a position of 2.0 meters and a position of 7.0 meters. Initially, our first line is going to look like that. It's a horizontal line. Then we're going to go from there to 7, and then we're going to have another horizontal line all the way to 17 seconds. So this is our position as a function of time, and I'm going to ask various questions. We're going to figure out various things about this particular motion. So for this first one, we'll say, what is the velocity from 0 to 5 seconds? When I ask for the velocity from 0 to 5 seconds, Lauren, am I referring to an instantaneous velocity or an average velocity? That is an average velocity. You know this because? The time period specifically being? That is the time duration, the time period, 0 to 5 seconds. Great. So it is an average velocity that I've asked for. We know average velocity is equal to the delta x over delta t. This is the time duration. Delta x, of course, delta always means final minus initial, so this is position final minus the position initial divided by the time final minus the time initial. In this particular case, our final is 5 seconds, our initial is 0 seconds, so the velocity then is going to be the position at 5 seconds minus the position at 0 seconds, divided by the time at 5 seconds minus the time at 0 seconds. Prescott, please read off the graph all of the information, the position at 5 seconds.
5 seconds is 2 meters.
The position at 0 seconds.
2 meters.
The time at 5 seconds.
5 seconds.
And the time at 0 seconds.
0 seconds.
Good. 2 minus 2 is 0. 0 divided by 5 is 0. The average velocity from 0 to 5 seconds, now the magnitude of the average velocity from 0 to 5 seconds is 0. Truth is, this is how you derive it, right? But how you actually should have been able to look at this and identify the average velocity from 0 to 5 seconds. Anyway, you should have just been able to look at the graph and know that. You can explain to me how, when just looking at the graph, you should know the average velocity from 0 to 5 seconds is 0. Joe.
It's a horizontal line.
I agree with that, but that doesn't answer the question. It gets to it, but I need more.
The distance remains constant during that time period.
The position remains constant, right? Not the distance, but the position. Okay, good.
Remains constant during that time period, and since position's on top, the change in position is 0.
Another way, right, absolutely. So we can tell, because it's a horizontal line, the position remains constant. Therefore, we're not moving. Therefore, the velocity is 0. Good. Another way to look at it. Rob?
Since the slope equals velocity, it has 0 slope.
Because the slope of a position versus time graph is velocity, this slope is 0, therefore the velocity is 0. Couple different ways to look at it. This is the mathematical way to look at it. Good. Let's look at another velocity. The velocity from 5 to 10 seconds. Velocity from 5 to 10 seconds. Chloe, am I asking for an average or an instantaneous velocity here? I don't know.
Because it's at a time.
time duration from 5 to 10 seconds. Again, the displacement over time, we know our final is at 10 seconds, our initial is at 5 seconds. So we have both 10 and 5 for our final subscripts and initial subscript. What is the position at 10 seconds, Kosek? What's the position at 5 seconds? 2, the time at 10 seconds? 10, the time at 5 seconds? Good. 7 minus 2 is 5, and 10 minus 5 is 5, so we get 1 with 2 sig figs, 1.0 meters per second. We now know the average velocity from 5 to 10 seconds is 1 meter per second. Colorina. What is the instantaneous velocity at 6 seconds? Instantaneous velocity at 6 seconds.
It's between 0 and 1 meter per second.
It's not. It's not between 0 and 1 meter per second. We actually know its value at this point. I'm asking for the instantaneous velocity at 6 seconds. Aileen.
It's 1.0 meters per second.
It's 1 meter per second. How do you know this, Aileen?
Because it's the slope at that point.
The slope at that particular point is also 1 meter per second. The slope of this line, right? Okay. What about the instantaneous velocity at 9 seconds? Emily. 1 meter per second again. What about the instantaneous velocity at 9.8765 seconds, Jimmy?
It's 1 meter per second.
Right. You can see the slope of the line all the way between 5 and 10 seconds is 1 meter per second. So any instantaneous velocity between those 2 points is going to be 1 meter per second, right? So you can see there are instances where the average velocity and the instantaneous velocity are going to be the same. Let's now figure out the average velocity from 0 to 17 seconds. We could figure it out from 10 to 17, but you should be able to identify that's equal to 0. At this point, I want to do the average velocity from 0 to 17 seconds. The displacement over time, position at 17 seconds minus the position initial, which is a position at 0 seconds. Time at 17 minus the time at 0 seconds. Please give me all of the numbers here. Houston, the position at 17 seconds.
7.
Minus the position at 0 seconds.
2.
Divided by the time at 17 seconds.
17.
Minus the time at 0 seconds.
0.
Which is 5 divided by 17. In this class, we do not leave things as fractions, so please give this to me as a number.
0.294.
That's plenty, thank you. So with sig figs, we'll go with 0.29 meters per second. So the magnitude of the average velocity from 0 to 17 seconds is 0.29 meters per second. How do I illustrate that on our graph? That the average velocity from 0 to 17 seconds is 0.29 meters per second. It's a way I can illustrate that on the graph. Herman.
Could you draw a line from 0.02 to 0.17 seconds?
If I were to draw a line from our initial point to our final point, the slope of that line would be 0.29 meters per second. That illustrates our average velocity for this entire trip. Does the instantaneous velocity for this trip ever equal the average velocity for the whole trip, according to our graph?
No.
What are our choices for instantaneous velocity for the entire trip?
There's just one.
No, there are 2 choices. What's one of them? Okay, you told me there was one, so what's the one?
In this case?
For the whole trip, what are our choices for instantaneous velocity?
Would it be 0.29?
0.29, no, that's the average velocity for the whole trip. I've now asked what's the what are the choices for instantaneous velocity for the whole trip? Luke, help him out.
1 meter per second.
And 0. From 0 to 5 seconds, our average velocity, or I'm sorry, instantaneous velocity is always 0. From 10 to 17, our instantaneous velocity is always 0 because the slope of both of those lines are 0. The instantaneous velocity from 5 to 10 seconds is always 1 meter per second because the slope is always 1 meter per second between 5 and 10 seconds. So in this particular case, according to the graph that we have, the instantaneous velocity will never actually equal the average velocity. Why is that physically impossible?
Because you have to accelerate at some point. You can't just instantly go to your top speed.
There has to be an acceleration here and an acceleration here. According to our graph, we actually have an undefined acceleration. The limit of it would be an infinite acceleration, but you're going suddenly from not moving at all to moving at 1 meter per second, which is impossible. You actually have to accelerate. If we were to draw this of something that was actually occurring, there would have to be curves here and a curve here. Mathematically, that's difficult to work with, especially in this class. That's why we don't really work with that, but realize this is not physically possible because you do have to accelerate. You have to go from 0 to 1 meter per second. So at some point here, the instantaneous velocity would be equal to the average. In our UAM equations, we have 5 UAM variables. 2 of those have to do with velocity, velocity initial and velocity final. Please tell me, Allison, velocity initial and velocity final, are those instantaneous velocities or average velocities? You know this because? I can almost hear it because it's?
The beginning time of the first point.
Then that's a specific time, right? The beginning and?
The final point.
Which is also a specific point. So notice we have 2 examples of instantaneous velocities that are part of the UAM equations, the initial velocity and the final velocity. That means that the velocity we've been talking about, we have an equation for delta x over delta t. This is for average velocity. Note the change in time in that. That is the time duration. So we already have examples of instantaneous and average velocity.